Welcome aboard to the second lesson of Sequences and Series. So it's pure chapter 3 for year 13, A-level Edexcel. The first lesson we looked at sequences, and now we're going to have a look at series. I'll explain the subtle difference in a moment, but before we do that, obviously there are some warm-up questions which you're probably coming to expect by now. So here they are, 4 of them to have a go at. Try these now on your own and press play on the video when you're ready to see the solutions to them and not before. Then if you need to make corrections, do so, but hopefully you won't need to make too many. So once you've had a go, press play. So let's have a look then together at warm-up question 1. We've got this curve, capital C, with this equation here, and we need to verify that C has a stationary point when x equals 4. So this is a throwback to what stationary points are and how you find them. So first of all, what we need to recall really is a stationary point implies that dy by dx equals 0 at that point. So in other words, we need to differentiate this function. So dy by dx, bring the power to the front and take 1 off the power. So 4 times 3 gives 12, x4 becomes x cubed. Bring the 3 to the front, multiply it by the minus 20, gives us minus 60, x cubed becomes x squared. Same with this 2, bring it to the front, multiply by the 24 to give 48. X squared just becomes x to the 1, which can just leave as x, and any constant term disappears, so this 7 just disappears. So now we can work out what dy by dx is when x equals 4. So just sub in x equals 4 into this expression for the derivative. So we're going to have 12 times 4 cubed minus 60 multiplied by 4 squared, then plus 48 times by 4. So we can work this out now, either in one go or just step by step. So 12 times 4 cubed, we can work this out fairly simply. So that's going to give us 768. Minus 60 times 4 squared, that's 60 times 16. That gives us 960, so minus 960. Then plus 48 times 4, so that's plus 192. That will come to exactly 0, or it should do. If it doesn't, I've miswrote this question. 768 minus 960 plus 192. Yep, comes to 0, equals 0. So therefore this shows that there's a stationary point at x equals 4. And part B is going to link to this. So part B, it says here we need to use a second derivative to determine the nature of this stationary point. So we need to differentiate the derivative. So we do d squared y over dx squared. So bring the 3 to the front, multiply by 12 gives 36. X cubed becomes x squared. Minus 60x squared becomes minus 120x. Plus 48x just becomes 48. So when x is 4, d squared y over dx squared gives us 36 multiplied by 4 squared minus 120 times 4 plus 48. So let's see what this is going to give. So 36 times 4 squared minus 120 times 4, then plus 48. That gives us 144. But if anything we need to make a note of is that this is greater than 0. And because it's greater than 0, that tells us that at x equals 4, we're going to have a minimum point. So therefore, it's a minimum point when x is equal to 4. And it's proven by the second derivative being positive. When the second derivative is negative, that shows that it's a maximum point. So that's warm-up question 1 done. Let's now have a look at warm-up question 2. Number 2, we've got this circle, and first of all we need to find the coordinates of the centre of this circle. So what we do here is we complete the square for the x terms and the y terms separately. So x squared minus 6x, and then y squared plus 8y. So what we have here, x squared minus 6x becomes x minus 3 squared. We minus off this 3 squared, so that becomes minus 9. We then do the same thing for the y terms. So we have y plus half the 8 is 4. Square that out, then minus off the 4 squared gives us minus 16. And that equals k. Now we may as well just neaten this up a bit. So we have x minus 3 squared plus y plus 4 squared. But minus 9 and minus 16 in total is subtracting 25. So we can add 25 to both sides to give k plus 25. But the centre of the circle comes from looking at these brackets here. So the centre of the circle is, we switch the sign, so the minus 3 is positive 3, and because the y bracket has a plus 4, that tells us the centre of the circle's y coordinate will be minus 4. So the centre of the circle is 3 minus 4. Then the range of possible values of k, well, we need to remember what this number here means. This value represents the radius squared. So the radius of a circle has to be greater than 0, otherwise it wouldn't exist. You can't have a circle with a negative radius, just doesn't make sense. And so this value here must be strictly greater than 0. So therefore, in terms of k, if we subtract 25 from both sides, we see that k has to be greater than negative 25. Let's have a look at warm-up question 3. The number of bacteria, n, in a petri dish after t days is modelled as n equals a t to the power b, where a and b are both positive constants. We have to show that this relationship can be expressed in this form here, log base 10 of n equals m log base 10 of t plus c, where m and c are some constants, and we need to also give m and c in terms of a and or b. So let's start off with n equals a t to the power b. So first of all, take logs of both sides. So take logs base 10, because we're told here it needs to be in terms of base 10, of both sides. So then we have log base 10 of capital N equals log base 10 of a t b. Now a and t to the power b is a product, so we need to remember that when we have logs, if we're taking the log of a product, that's the same of the log of the individual components. So this can be split into log base 10 of a plus log base 10 of a t to the power b. Next, we need to remember as well that when we're taking logs of something to a power, whoops, sorry, my mistake, silly. We've already taken logs there, so that just becomes like so. So just have log base 10 t to the b, apologies. So when we're taking logs of something to a power, the power comes down to the front and multiplies the log. So this b comes to the front before the log. So we have plus b lots of log base 10 to the power of t. Finally, this can be slightly reordered. Like so. We can now compare and contrast what we have here compared to what we need over there. So if we just have a look and work this out, so we've got log base 10 n first, which is obviously this. Then we have log 10 to the t here. So the stuff in front, the m, is b. So therefore, m equals b, and c must be this thing at the end. So c must be log base 10 of a. So we've succeeded in writing it in the right form, and as well we've expressed m and c in terms of a and b as required. Let's now finally have a look at the final warm-up question 4. So for number 4, we're told that the first and fourth terms of an arithmetic sequence are k minus 4 and k squared, where k is greater than 0. We're told that the common difference is 8. We need to find the nth term rule for the sequence. So first and fourth terms, to go from the first to the fourth, have gone up 3 terms. So if we've gone up 3 terms, the second, the third and the fourth, that'll be an increase of 3 multiplied by the common difference, which is 8. So in other words, what we're saying is the difference between the fourth term, which is k squared, and the first term, which is k minus 4, the difference is going to be 24. 3 times 8 is 24. So we can write this down. So k squared minus the first term equals 3 times by 8, where 8 is a common difference. The first term is k minus 4, and the fourth term is k squared. So if we neaten this up now, so we have k squared minus k minus minus 4, so that's plus 4, equals 3 times 8, which is 24. Subtract 24 from both sides, we get k squared minus k minus 20 equals 0. What can we do here? Well, this will actually factorise. So 2 numbers that multiply to negative 20 and add up to negative 1, that's going to be a positive 4 and a negative 5. So k plus 4, k minus 5 equals 0. So therefore, to solve this, we have k is either minus 4 or k equals 5. But we're told here that k has to actually be greater than 0. So because of that, we can eliminate this option because that's a negative. Therefore, k equals 5. So this sequence is going to go, well, k minus 4 will now be 5 minus 4, which is 1. The common difference is 8, so it'll be 1, 9, 9 add 8 is 17, then 17 add 8 is 25, and so on. And if you check the fourth term, it's k squared. 5 squared is 25, so it does check out as you'd expect. We can now apply some GCSE ideas to this. So the nth term here is actually quite straightforward to work out. So the nth term, the sequence is going up in 8s, so I'll have something to do with 8n. but this is 7 lower each time from the 8 times table, so it'll be A10 minus 7. Now let's have a look at the main bit of this lesson. So, we need to talk about arithmetic series now. So, simply put, an arithmetic series is the sum of the terms of an arithmetic sequence. So the distinction between a sequence and series is going to be illustrated in these two below examples. So to start off with, there's a sequence. That's a sequence 2n plus 3. 5, 7, 9, 11, 13. It's a sequence of numbers. Whereas a series would be the sum of that sequence. So the series version would be this. 5 add 7, add 9, add 11, add 13. And there are some calculations we need to know how to perform in terms of series rather than just sequences. So, how to sum arithmetic series? Well, a bit of an example for you, a very famous example before we talk about how to do this. And it starts with Carl Gauss. He lived from 1777 to 1855, and he was a well-known child prodigy even in his lifetime, and he's one of the most famous and influential mathematicians of all time, up there with the likes of Archimedes, with Sir Isaac Newton, and others. So this is what he looked like with his little hat on. So in his memorial on Gauss, his biographer, Wolfgang Sartorius van Volterhausen, claimed that when Gauss was only 7 years old, he confidently solved an arithmetic series problem faster than anyone else in his class of 100 plus students. So many versions of this story have been retold since that time, with various details regarding what the series was. We don't even know for sure if it was true, but given the status of Gauss, I personally do believe it is true. But the most frequent version is that he solved the classical problem of adding all the integers together from 1 to 100. And he gave this answer, according to most, incredibly quickly, to the point where the teacher was startled beyond belief. So, how did he do this? Well, let's discuss Gauss's method, or a supposed method that he used. So let's show that the sum of the first 100 natural numbers, as Gauss presumably worked out, is 5050, without adding them up one by one and taking forever about it. So what we'll do, we'll call the sum of the first 100 natural numbers, we'll call that S subscript 100, which stands for the sum of the first 100. So first of all, if we imagine the sum of the 100 natural numbers like this is obviously fairly self-explanatory. So 1 plus 2 plus 3 plus etc., all the numbers in between, then finally plus 98 plus 99 plus 100. So an insight of genius for a 7-year-old, and a few different ideas have been put forward to how he did it, or two ideas mainly. One is that Gauss may have paired up the numbers from end to end. So for example, 1 plus 100 is 101. 2 add 99 again is 101. 3 plus 98 is 101. So one idea of what Gauss probably did is he realised, well, you've got 100 numbers, so you're going to have 50 pairs of numbers. If you pair them up from end to end, you're going to have 50 pairs which all total 101. So the answer will be 50 multiplied by 101. 5 times 101 is 505. Add on that 0, gives us 5050. Another possibility of what he did, and this idea is going to have more currency and is going to be much more versatile for our problems, is what he may have done is reverse the order. So this is what I'm going to do here. So just rewriting it in the reverse order. So start with 100, then run down accordingly. 99 plus 98 plus 97, 96, and so on and so on. And get towards the end, plus 3, plus 2, plus 1. Now what we can choose to do is we can add both rows together. So on the left-hand side of the equal sign, we've got S100 plus another S100. So two lots of the sum of the first 100 natural numbers would be 101 plus 101 plus 101 plus 101 plus 101 plus 101. So that's going to be 100 lots of 101. So two lots of the sum of the first 100 numbers is going to be 100 multiplied by 101. So therefore the sum of the first 100 numbers, we can divide both sides of this by 2. Now I'm going to leave this in a different form, so hopefully we can see the link for later. So 100 over 2, okay, and then 101 we could think of as 1 plus 100. So if we're summing n numbers, it's this number here divided by 2, so it's going to be n over 2. The 1 is the first term, and think of 100 as being the last term. So this generalization we're going to use later. But anyway, in terms of actually summing them, 100 over 2 is 50. 1 plus 100 is 101. So again, we have 5050. But what we can do is we can generalize this for any arithmetic series. So for the particular one of the sum of the first 100 natural numbers, this is how Gauss did it. How can we generalize this for summing up any arithmetic series? And this is what we're going to do here, and we're going to prove a very powerful result. So prove that the sum of the first n terms of an arithmetic series, this is the result we want to show here. So we're going to call it Sn. I'm going to adapt Gauss's method. So the first term is A. The second term, the common difference is D, so the next term along will be the first term plus a difference of D. The second term will be this one plus an extra D, so that'll be A plus 2D. And now I'm going to just jump on to the very last one here. We need to remember what the nth term is for an arithmetic sequence from the first lesson. The nth term, the final term here out of n, is A plus n minus 1 lots of D. So if we just reverse this and subtract a D each time, this one here would be A plus n minus 2 lots of D. And this one here would be A plus n minus 3 lots of D. Then, like we did before, I'm going to reverse it. Reverse the order entirely. Then this term I'm going to put below A plus D. So I have A plus n minus 2 lots of D. This one, A plus n minus 3 lots of D. And so on and so on. And finally here, I have A plus 2D, A plus 1D, and finally, the first and smallest term would be A. So now what we can do, like we did before, is to add these together. So two lots of the sum of the first n numbers in an arithmetic series. So A plus A is going to be 2A plus n minus 1 lots of D. Here, a plus a again gives us 2a. Now if you want to expand the brackets to convince yourselves, by all means you can. But what we'd have here, expand the brackets, we'd have nd minus 2d plus this d would be nd minus 1d, which again would give us, in factorised form, n minus 1 lots of d overall. This one, a plus a, is 2a, nd minus 3d, but plus an extra 2d's, again overall would give us n minus 1 lots of d. So hopefully now you can see what's happening. We've got the same thing again and again and again. So we've got another 2a plus n minus 1 lots of d, and another 2a plus n minus 1 lots of d, and the last time a plus a, another 2a plus n minus 1 lots of d. What you should be able to discover here is we've therefore got n lots of this 2a plus n minus 1 lots of d. So we can simplify this line by saying 2 lots of Sn equals n lots of this 2a plus n minus 1 lots of d. We've got this thing here n times. So we've got n lots of it all together. So the final step is just simply to divide both sides by 2. So therefore, Sn, the sum of the first n terms of any arithmetic series, is the number of terms divided by 2 multiplied by 2 lots of the first term plus n minus 1 multiplied by the common difference between successive terms in the sequence. Now, another way we can think of this is if I just were to partition what's inside these squared brackets. So I've got n over 2, then a plus n minus 1 lots of d. And if you think of it in this way, then the nth term of an arithmetic series, arithmetic sequence rather, is a plus n minus 1 lots of d. That's the last term, and obviously this here is the first term. And so although this here is the main result we want, another useful thing we can think about is it's actually half n multiplied by the first plus the last term. So if we just simplify this here and just call it L for last, we can say this result here of n over 2, 2a plus n minus 1 lots of d, can be expressed as n over 2, a plus L, where a is the first term and L stands for the last. And that's a much neater form of this result, although generally speaking, this first result, although harder to look at, it's a bit more awkward, is more versatile. Now we've got that out of the way, let's apply it to some worked examples. So, worked example 1. Find the sum of the first 50 terms of the series 12 plus 15 plus 18 plus 21 plus so on and so on. So, we can clearly see here that the first term is 12. So I'm just going to write down that a equals 12. And the common difference, well, we can see from 12 up to 15 we've added 3. From 15 to 18 we've added 3 as well. So it's going up in 3. So the common difference is positive 3, because as we go from one to the other, we're adding 3 each time. So like I say again, a is 12 and the common difference is 3. And just to remind you of that last result, here's how we can work out the sum of the first n terms of an arithmetic series. So if we just plug this in, by the way as well, we know that the number of terms we want to find is 50, because it says here the first 50 terms. So I'll add this in as well, n equals 50. So therefore the sum of the first 50 is going to be n over 2, so that's 50 over 2, 2 multiplied by the first term, so that's 2 times 12. Then we're going to add n minus 1, which is going to be 50 minus 1, multiplied by the common difference, which is 3. So all I've done here is we've just plugged in these terms. So n is 3, a is 12, and the number of terms, n, is 50. So we can use a calculator for this now. And I'll show you another trick this calculator can do as well in a moment. So, what we're going to have, maybe it's bigger so you can see it. So 50 over 2, 2 times 12 plus 50 minus 1 lots of 3. Close brackets. And we get 4275. Now we're going to have a lesson on sigma notation, but I'm going to just skip ahead here. So this series here, if you imagine it as a sequence, so this is going a bit above and beyond what we need to know today, but it's worth mentioning. So 12, 15, 18, 21. Then quite clearly the nth term of this is going up in threes, so it'll be 3n, but the first term, the 12, is 9 higher than 3, so it's going to be 3n plus 9. So what we can do here is we can use a calculator function. So we want the sum of the first 50 terms. So sum is this sigma symbol. First 50 terms means we want it to go from the first term, if I call x the term number, so x equals 1, up to 50, 3x plus 9, then what this means the sum of the terms from the first to the 50th of 3x plus 9. I can't stress enough, I'll have a full lesson on this, but just to skip ahead, just to introduce this calculator function to you. So if we go and press Shift X, we want to go from the first term up to the 50th, and the sequence, the nth term of a sequence, is, in terms of x, 3x plus 9. So for example, when x is 1, 3 times 1 plus 9 is 12. When x is 2, 3 times 2 plus 9 is 15. So it's going to add up 12 plus 15 plus 18 plus 21, all the way up to and including the 50th term. So we do need to work out the nth term to use this strategy, but if we sub this in, press equals, it works out for us. We get 4275. So that was worth a mention, I think. Let's have a look at worked example question 2. Find the sum of the series 7 plus 13 plus 19 plus 25 plus all the way up to 73. Now we're not told how many terms this one has. We're just told that it begins at 7 and ends at 73. Now for this example, what's worth considering is this form of the result. The sum of the first n terms, no matter how many terms that will be, is n over 2 multiplied by the first plus the last. But again, we don't know how many terms this is. So what we can do here is think about working out how many terms we're dealing with. So remember, the nth term is always a plus n minus 1 lots of d, like so. Now we know the first term is 7, because we've got it here, it says a is 7, because we're starting at the 7th. The common difference we can see quite easily. This sequence here is increasing in 6s. So the common difference, d, equals 6. So we can apply this to 73. So if we just put, using this here for the nth term, so 73 equals the first term, 7, plus n minus 1 multiplied by 6. So if we subtract 7 from both sides, we get 66 equals 6 lots of n minus 1. Then if we divide through by 6, 11 equals n minus 1. So therefore, adding 1 to both sides, n equals 12. So in other words, we've got 12 terms. So we can either use this form or the original form from worked example 1. It doesn't really matter which form we use, but just to show you this one will work, we can say that therefore the sum of these first 12 terms is going to be 12 over 2, the first term, which is 7, plus the last term, which is 73. So if we just calculate this now, so 12 over 2, and brackets 7 add 73, we get 480. Now again, I'll show you the sigma notation for this one. So for this sequence here, the nth term is going up in 6s, so it's going to be something to do with 6n. But 7 is 1 higher than 6, so it's going to be 6n plus 1. So if we were to do the sum of the first 12 numbers, the first to the 12th of 6x plus 1, using this calculator method, we'd get the same result. So it's just good to have a bit of versatility in terms of tackling these questions. If we can do it more than one way, that's got to be better, yes? So shift this to get the sigma notation in. So 6x plus 1 is our x term, because it uses x rather than n the calculator, but fair enough. Go from 1 up to 12, press equals, and there you have 480 again. So the same result, just a different way of doing it using the calculator. Let's have a look at the third worked example. So this one, find the least number of terms required for this sum, 3 plus 8 plus 13 plus 18 and so on, to exceed 1000. So again, we need to remember what the sum of the first n terms is. So generally speaking, the sum of the first n terms is n over 2, 2a plus n minus 1 lots of d. So here, let's fill in what we know. The first term, a, is 3. The common difference is 5, because it's going up in 5s. And the number of terms, well, that's what we're trying to work out. We're trying to work out how many terms it takes for this thing here to go beyond 1000. So in our case, Sn is going to be n over 2, big squared brackets, 2 times 3 plus n minus 1 times 5, and that's got to be bigger than 1000. So that's our starting point. So let's now neaten this up. So we've got n over 2, 2 times 3 is 6, n minus 1 times 5, that's 5 lots of n minus 1. That needs to be greater than 1000. Expand the brackets. So n over 2, well, we could expand the brackets, or I'm thinking what we could do, we could multiply both sides of this by 2 actually, just get rid of that fraction. Let's multiply both sides by 2. That will then give us n, 6 plus 5 lots of n minus 1, is going to be greater than 2000. Let's give myself a bit more space. Now we can expand. So n times 6 is 6n, n times 5 is 5n, n minus 1 needs to be greater than 2000. So 6n, 5n times n is 5n squared, 5n times minus 1 is minus 5n, needs to be greater than 2000. So finally, let's neaten this up. So we've got 5n squared, 6n minus 5n still leaves us with a positive n, and if we subtract 2000 from both sides, then this here needs to be greater than 0. So we've got a quadratic inequality to solve, and the good thing to know is the class whiz can do this for us very comfortably indeed. So if we get the calculator, press menu and scroll along until we get to this here, inequality. Press equals. Now it's a quadratic inequality because it's an inequality of highest power 2. So press 2. Now we've got it in this form where we want the quadratic stuff to be greater than 0. So we want option 1 here. So press option 1. So how many n squareds do we have? We've got 5n squared. We've got 1n, then minus 2000. Press equals, then equals again to bang it in. So we need x to be less than, well in our case n. So we've got n less than minus 20.1-ish. If we scroll along, or we want x to be greater than 19.9. Oops, not x, I mean n, my mistake. Now, the number of terms has got to be a positive value. You can't have like a minus 20 terms, so we're looking at this here. So the number of terms needs to be more than 19.9, but again the term number has to be a whole number, so we can deduce from this that if it needs to be more than 19 terms, the smallest integer value that satisfies this is 20. So we need 20 terms. Let's have a look at another one. Worked example 4. For example 4, we've got an increasing arithmetic sequence. It's got a second, a third, and a fourth term, like so. Now, importantly, it's not starting from the first term. So this is the second one, that's the third, and this is the fourth. So it's an arithmetic sequence, so we can use this to our advantage straight away. So therefore, we know that the difference between the third and the second will be the same as the difference in between the fourth and the third term. The difference is the same, it's a common difference. So the difference in between the third and the second term is going to be the third term, 4k, minus the second term, k plus 7. And the difference between the fourth and the third is going to be k squared plus 3 minus 4k. So let's neaten this up. So 4k minus k gives us 3k, then minus 7. Over here we're going to have k squared minus 4k plus 3. Rearrange it so everything's on the same side of the equation. So if we subtract 3k from both sides, we're going to have k squared minus 7k. But if we add 7 to both sides, 3 plus 7 gives us 10. This will now factorise quite nicely. We want two numbers which multiply together to give 10, but when we add them together give negative 7. So those two numbers would be negative 2 and negative 5. So therefore k equals 2 or k equals 5. Now we're told here that this sequence is increasing. So we need to just check which one of these values of k, maybe both, would give us an increasing sequence. So if k is 2, is that going to work? If k is 2, 2 plus 9, sorry, 2 plus 7 is 9. 4 times k, 4 times 2 is 8. And then k squared, 2 squared is 4, plus 3 is 7. So that clearly is not going to be an increasing sequence. So let's try, just to make sure, if k is 5. So yeah, we've tried k being 2, it's not increasing, so we need to rule off k being equal to 2. But if k equals 5, then k plus 7 is going to be 5 plus 7, which is 12. If k is 5, 4 times 5 is 20. And 5 squared plus 3, 25 plus 3 gives 28. That does work, so therefore our k needs to be 5. Now that's the second term. The second term is 12. So the first term, clearly this is going up in 8s, so the first term would have to be 4. So, now we know that, we can proceed quite easily, in fact. So the sum of the first n terms is n over 2, 2a plus n minus 1 lots of d. Now we can just sub in that the first term is 4, and we also can see that the common difference is 8. This is going up in 8s. So if we sub in a is 4 and d equals 8 into this expression, Sn is n over 2, 2 times 4 plus d, which is 8, lots of n minus 1. So let's neaten this up. N over 2. 2 times 4 is 8. Then 8 times n is 8n, and 8 times minus 1 is minus 8. So the 8's in the brackets are going to cancel. So we have n over 2, brackets 8n. So if we multiply this out, n over 2 times 8 gives 4n, then times an extra n gives us 4n squared. And 4n squared, that's 2n all squared. So because n is an integer, 2n is an integer, and this whole thing here squared is therefore a square number. So therefore Sn is a square number. It's basically 2n squared. Now we can finally have a look at worked example number 5. Last but not least, worked example number 5. We're told the 6th term of a sequence is 19 and the 12th term is 49. The sum of the first n terms is 4,890. Part A, we need to show that this horrible quadratic equation is the case. So the 6th term, we're told, is 19. Up to the 12th term is 49. So let's think what this means. From the 12th to the 6th, that's an increase of 6 terms. And if it's increased by 6 terms, then the common difference is d. So the difference will be 6d. So therefore, the difference between the 6th and the 12th, which is 49 minus 19, that's going to equal 6 times the common difference. So 30 equals 60. So therefore the common difference has to be 5. And you can test this out. If the 6th is 19, the 7th would be 24, 8th would be 29, 9th would be 34, 10th would be 39, just adding 5 each time, 11th would be 44, and the 12th would be 49. So a difference of 5 would fit in perfectly. So you could even work this out the long way. This is how you can do it using this idea of a common difference. So d equals 5. So let's just sub this into the 6th term. So the 6th term, if we just use this idea that the nth term un equals a plus n minus 1 lots of d, and plug it into the 6th term. So if we're looking at the 6th term, and the 6th term we're told is 9. We can work, sorry, 19 I mean to say. We can work out what the first term is. So 19 equals a, whatever the first term is, plus d, 5 lots of n minus 1. So the 6th term, that means 6 minus 1. So simplify this a bit. So 19 equals a, 6 minus 1 is 5, 5 times 5 is 25. So therefore a, the first term, must be 19 minus 25, which is minus 6. So we've worked out the common difference is 5, and the first term must be minus 6. So we can now use the sum of the first n terms. So just remember that Sn equals n over 2 brackets 2a plus n minus 1 lots of d. That's what we need to be employing and using again. So here though, we're told what Sn is. We're told the sum of the first n terms is 8490. So that's what our sum is. So therefore 8490, just plugging into this formula, equals n over 2 brackets 2 lots of a, so that's 2 times minus 6, because you worked out down here that a was minus 6, plus n minus 1 lots of d, which we worked out was 5 from the first step. By the way, this is part A, I should say. So the common difference is 5, that's where this 5 comes from. So we can now set about proving part A. So if we now multiply both sides by 2, what's 8490 times 2? Well, let's see. 8490 multiplied by 2 gives us 16980. So 16980 equals n. Then 2 times minus 6 is minus 12. N minus 1 times 5. That's going to give us n times 5, which is 5n. Minus 1 times 5 is minus 5. So 16980. N times 5n gives 5n squared. The total of the negative numbers in these brackets is minus 12 minus another 5, that's minus 17. So n multiplied by minus 17 gives minus 17n. Therefore, subtracting 16,980 from both sides, we can see that 5n squared minus 17n minus 16,980 must equal 0. So that's proven what we needed to show all along. So we've done that part. Part B is now really easy because we've got the class whiz which can do the legwork for us. So what's the value of n which will satisfy this? So menu, option A, it's a polynomial we're trying to solve. It's degree 2 because it's quadratic. Let's just type in the coefficients. So 5 is the squared term, minus 17 is the n term. The constant term is this massively negative minus 16,980. Press equals and equals again. So either n is 60 or n is minus 56.6. Therefore n equals 60, because obviously the nth term, n has to be a natural number. It's either the first term, the second, or the third. It can't be negative, and it certainly can't be a fractional term either. So we reject this one. We say that therefore n must be 60. There must be 60 terms in this sequence if the sum of it is 8490. And just to return to the previous idea of using the sigma notation, which I use in worked example 1 and 2, if you wanted to, you wouldn't need to, but just showing you how useful this can be as a double check. So the common difference is 5, so the sequence is going to be 5x. It's going to be going up in 5, like the 5 times table. Now the first term here was negative 6, and minus 6 is 11 lower than 5. So this would be an expression for the nth term of this sequence. And we want to show if n is 60, if the sum of the first 60 terms should give 8490. And if we press this, just to verify, you can see indeed that it is 8490. It checks out and it's true. That's all the worked examples for me. Now it's over for you lot to try some. So page 64, exercise 3b in the year 13 pure book. Try these sections from question 1, question 2 A to C, finish can stomach it, all of them from question 3 through to question 13. Thanks for listening. I hope you have found this useful. Each time you try a question, check its answer as soon as you've completed it, check regularly and ask me if you're unsure. Once again, I do appreciate you listening. Please do consider subscribing and you'll hear from me again soon enough. Bye for now.